Bonsoir Stella, j'espère que tu vas bien. Avant de commencer à traiter les exercices de physique que tu m'as envoyés, je vais d'abord essayer de t'expliquer un principe très simple, très important pour que tu puisses bien comprendre les exercices qui ont à y voir avec tout ce qui est heat capacity, specific latent heat et tout ça. Il faut que tu comprennes ce principe très important. Je ne sais pas si vos enseignants ont eu à vous dire cela, mais je vais expliquer cela ici. Ok. Supposons que, let's assume we have a substance which is capable of existing in three states. Let's say the substance can exist in state 1, which is the solid state, state 2, which is the liquid state, state 3, which is the gaseous state. And let's say the substance is at this temperature in the solid state, it is at this temperature in the liquid state, and at this temperature in the gaseous state. Now, the question is that they are asking you to calculate the total energy required to convert this substance from this state, solid state, at this temperature to the gaseous state at this temperature. For you to be capable of doing, they are asking you to calculate what will be the energy, that is the energy required to convert this substance from this state at this temperature to this state, this gaseous state at this temperature. Now, for you to be capable of doing this exercise, it's very important for you to master some concepts. First of all, I'll recall some very important concepts. Heat capacity, like for example, the first concept I'm going to recall is heat capacity. I think you know the definition of heat capacity. It is simply the amount of thermal energy, thermal or heat energy required to produce a unique rise of temperature in a body. When you are defining heat capacity, you don't mention the mass. It is simply the amount of heat energy or thermal energy required to produce a unique rise in temperature in a body. You understand? So, the heat capacity, the symbol is what? The heat capacity, the symbol is capital C. The symbol is always capital C. And the formula is what? You can remember this formula for you to easily make big C the subject. Remember this formula, Q equals to C delta theta. Q equals to big C delta theta. From there, you can make big C the subject. This is the heat capacity. You understand? Now, for specific heat capacity, whenever you are defining specific heat capacity, you have to mention mass inside your definition. So, specific heat capacity, if I'm to define it, I'm sure you know the definition. It is the heat energy or thermal energy required to produce a unit rise of temperature in a unit mass of a body. You have to mention mass in a unit mass of a body. The difference with heat capacity is that when we were defining heat capacity, we said it is the thermal energy required, the thermal energy or heat energy required to produce a unit rise of temperature in a body, not in a unit mass of a body. You understand? So, for the formula of symbol of specific heat capacity, it is small c. And to know how to calculate it, simply remember this formula. Heat transfer, heat required is equals to what? MC delta theta, where this small c is what? The specific heat capacity. Q is measured in joules, delta theta is measured in Kelvin, and M is measured in what? Kilogram. M is the mass. Now, that's the first thing I wanted you to remember. The next thing I want you to remember is what is called latent heat. What is called latent heat? Now, to define latent heat is simply the, if I would say, the thermal energy absorbed or released by a substance when it changes states. Latent heat is simply what? the thermal energy absorbed or released by a substance when it changes state, only state, without a change in temperature. So when a substance changes states without a change in temperature, that substance was capable of doing it because of what? Latent heat. So it is latent heat is the energy absorbed or released by a substance when it is the energy absorbed or released by a substance when it changes states without a change in temperature. That's the definition of latent heat. Now, there is a more specific, to be more specific, we are going to see what we call specific latent heat. The symbol is what? Small l. The formula to calculate specific latent heat is what? Q. That is, this Q is the energy absorbed or the energy released by the substance when it changes state without a change in temperature. This is the mass of the substance, and this is the specific latent heat. Now, if you are asked to define specific latent heat, it is simply the thermal energy absorbed or released. Specific latent heat is simply, specific latent heat is simply the thermal energy required to change the state of a unit mass of a substance. The energy required to change the state of a unit mass of a substance without a change in temperature. Now, there are two types of specific latent heat. We have specific latent heat of fusion and specific latent heat of vaporization. Why are they only two types? Because we know that fundamentally there exist three states of matter. We have the solid state, the liquid state, and the gaseous state. To see if latent heat, if we talk of latent heat whenever we are changing states, it means that to leave from solid to liquid, there must be a latent heat that exists here. To leave from liquid to gaseous state, there must be a certain latent heat that exists here. And you see that the two types of specific latent heat are what? Specific latent heat of fusion and specific latent heat of what? Vaporization. Whenever you are leaving from solid, either from solid to liquid or from liquid to solid, we talk of what? Specific latent heat of fusion. So when you leave from solid, the solid state to the liquid state, or from the liquid state to the solid state, we talk of specific latent heat of fusion. Whenever you are leaving from the liquid state to the gaseous state, or from the gaseous state into the liquid state, we talk of specific latent heat of vaporization, small l, L small subscript v. So it's very important for you to understand that. So that this is the formula to calculate the specific. So the symbol for specific latent heat of fusion is L small f, and the symbol for specific latent heat of vaporization is L small v. To calculate the energy absorbed or released whenever you are leaving from solid to liquid, this is the formula. Energy absorbed or released equals to what? The mass of the substance times what? The specific latent heat of fusion. To calculate the heat absorbed or released when you are leaving from liquid to gaseous state, or from gaseous to liquid state, the formula is heat absorbed or released equals to what? Mass of substance times times specific latent heat of vaporization. Now, I want you to remember this very important rule I'll give to you. What can you say about the difference between specific heat capacity or heat capacity and specific latent heats? The main difference that exists between them is that we are going to talk of heat capacity or specific heat capacity whenever there is a change in temperature. When there is no change in temperature, we cannot talk of this, because look at them. Look at this. In their formulas, what do we have? There is change in temperature. The heat here, the form heat here, heat transferred here is how? Heat transferred here is a function of what? temperature. So whenever there is a change in temperature, we shall talk of either specific heat capacity or heat capacity. But whenever there is a change in state without a change in temperature, we shall talk of what? Specific latent heat. Because look at the formula. The formula does not depend on temperature. So whenever there is a change in state without a change in temperature, we shall talk of what? So when there is a change in state, we talk of what? Specific latent heat. We talk of specific latent heat. You understand? Whenever there is a change in temperature, we shall talk of specific heat capacity or specific or heat capacity. You understand? So take note of that. So I'm going to explain a very small principle now. Let's take now this small illustration. Our question is to calculate the total energy that will be needed to convert this substance this substance state one from state one, that is the solid state, to the gaseous state. How are we going to calculate this total energy? Let me explain how we're going to do this. This is our substance. This is state one. Look at this. I'm going to illustrate something very simple. This is state one, that is the solid state. The solid state. This is state two. State two, which is the liquid state. This is state 3, which is the gaseous state. The gaseous state. This state is at theta 1, this state is at theta 2, and this state is at theta 3. Now, our aim is to calculate the substance is leaving from this solid state into what? The gaseous state. Now, let me draw a line. Okay, our aim, what is the energy required to convert this substance from state 1 to state 3? Let me draw a line here like this, and like this. Okay, let's first analyze this phase, this first phase. So I will call this phase phase 1, and I will call this phase phase 2. Okay, because I call it phase 1 because the substance is leaving from one state to another state, and here it is also leaving from one state to another state. This is phase 1 and phase 2. Now, what really happens? What really happens in this first state? In this first state, what happens is that the substance, whenever the substance will first leave from what? From the solid state to the liquid state. When you have, for example, ice, when ice starts melting, it will leave from the solid state to the liquid state at the same temperature theta 1. So ice will first, if I apply heat to this system, ice will first leave this solid state into the liquid state at the same temperature. It will first become liquid. Now, this same this liquid at the temperature theta 1, this liquid, this ice, which is already liquid, will leave now the temperature what? This ice, let me wipe this. So as I said, whenever heat is added to this system, the ice or the solid or the substance will first leave what? The solid state to the liquid state at the same temperature. Understand the process I'm explaining. It will first leave the solid state to the liquid state at the same temperature theta 1. At theta 1, at the same temperature theta 1. Now, when it is already liquid, the liquid, when it's already liquid, it will leave now from what? Theta 1 to what? Theta 2. A substance will not leave this state to this state at the substance will not leave the solid state directly into the liquid state with a change in temperature. No. For a substance to change temperature, for this substance to change temperature, it will first leave the solid state into the liquid state at the same temperature. Then when it becomes liquid, that is, it's already here, it will then leave the temperature at which it was, theta 1, into what? The temperature theta 2. So we know already the two processes that are taking place here. So let's call the energy that we want to calculate, the energy required to convert it from solid state into liquid state. Let's call it Q1. So we have to calculate Q1 here. Now, Q2 will be the energy required to convert what? The liquid we have obtained here at theta 1 into what? The temperature theta 2. We know already the amount, so the total energy required to convert this substance from state 1 to state 2 will be what? Q1 plus Q2. So we know already the total energy that is required in phase 1. I hope you understood what I said. Let's now go to the second phase. In the second phase, we're going to apply the same procedure. In the second phase, the substance is already a liquid at this temperature. The substance will first leave what? The liquid state into what? The gaseous state. Into the gaseous state at the same temperature. At what temperature was it? At the same temperature theta 2. When it is already a gas at this temperature, that's when it will then leave this temperature into this temperature. So when it is already a gas, it will do what? It will leave the temperature theta 2 into what? The temperature theta 3. That's how substances behave. So here, the energy that will be needed to convert it, the substance from the liquid to the gaseous state at the same temperature will be called what? Q3. Let's call it Q3. And the energy that will be needed to convert the substance from the gas state, that will be needed to convert the gas that we have obtained from temperature theta 2 to theta 3 will be called what? Q4. So in phase 2, the total energy used required is what? Q3 plus Q4. Now, they are asking you what is the total energy required to convert this substance from state 1 at theta 1 to state 3 at theta 3. It's very simple. The total energy Q will be simply equals to what? Q1 plus Q2 plus Q3 plus Q4. That is simply what they are asking to calculate. That's simply what they are asking you to calculate. So, what I want you, there is something very important I want to mention again. How are we going to calculate this Q1? What happens here? The substance is doing what? It is changing state. So, what will be the formula we are supposed to use here? It's changing state from what? Solid to liquid. So, what is involved here is what? Latent heat of fusion. So, to calculate Q1, Q1 will be equals to what? Mass of substance times latent heat of fusion. Here, the substance is already a liquid, but it is doing what? Changing temperature. It is not changing state. So, what we are supposed to use here is what? We are going to calculate Q2. Q2 will be equals to what? We are going to use the formula of what? Specific latent heat, simply. No, specific heat capacity. So, Q2 will be equals to what? M delta theta. M small c delta theta. You understand? M small c delta theta. Where delta theta here will be what? Theta 2 minus theta 1. Very simple. Is that okay? In the phase 2, what will be Q3 here? Q3 will be equals to what? the substance is changing state. It is leaving from liquid to gas. So since it is changing state, what will be involved here? Latent heat of vaporization. So Q3 will be the mass of substance times latent heat of what? Vaporization. Here, the substance is changing temperature, not state. So Q4 will be equals to what? M small c delta theta, where delta theta equals to what? Theta 3 minus theta 2. I hope you understood what I did. So always try to break down things like this. Whenever you are given an exercise, always try to break down things like this. If you are capable of breaking down things like this, that will be very helpful to you. It will help you a lot. You will always understand all the mechanisms that are going on in the exercise that is being given to you. So try to go through this video again. Master well what I just explained. Master well what I just explained. Because in the exercises, that's exactly what we're going to be applying. So master well what I just explained. It's very important, especially this last concept I explained. This is a concept that most students don't understand. When we talk of when there is a change, whenever a substance is leaving from one state to another, it first changes states. When a substance is leaving, for example, from the solid state to the liquid state, it will first change state at the same temperature. So if it is leaving from solid to liquid, it changes state first of all from solid to liquid at this temperature. Before, when it's already liquid, that's when it will change temperature from theta 1 to theta 2. Be very careful. That's the same procedure here. To leave from liquid to gas, to leave from liquid at theta 2 to gas at theta 3, the substance first changes state from liquid to gas at the same temperature theta 2. When it's already a gas, that's when it then changes temperature from theta 2 to theta 3. And when there is a change of state, what is involved is latent heat of fusion, is latent heat, or specific latent heat. But when there is a change in temperature, it is specific heat capacity that is involved. So be very, very careful. Master this explanation I just gave to you. So let's see ourselves in the next video for us to solve the exercises. See you in the next video.